Hey guys, in this video we're going to be going through the CycleGAN architecture. In the last video we went through the pix-to-pix architecture for image translation, and in this video we're going to take that architecture a step up and we're going to be talking about the CycleGAN architecture. Now the CycleGAN architecture fixes a fundamental problem that pix-to-pix faces, which is that pix-to-pix needs paired image datasets. Now, what is that, and why is that a problem, and how does CycleGAN solve that? Well, we'll get into that shortly. But let's first refresh ourselves on what is image-to-image translation. Image-to-image translation is when we want to translate an image from one domain into another domain. So I have some examples here. So in this case, we want to translate black and white images to color images, or we can translate day images to night images, or we can translate edges to photos. You know, the limits of what you can do here are pretty much unbounded. So that's what image to image translation is. So just to recap on the pix-to-pix architecture, we'll also go through that as well. So the pix-to-pix architecture needs XY image pairs. And this is supervised learning because we have features, which is our X, and Y, which is our images in the other domain. So X is images from domain A and Y is images from domain B. So this is supervised learning. And the really key thing to note here is that these have to be paired up. So we need to have these pairs as in our data set. So we need to have this image and this image, which corresponds to the exact translation of that image. And that's one key thing to know about the pix-to-pix architecture. So if you watched the last video, then you will be familiar with this diagram here, where we have a picture of edges, and we pass that to a generator. We get the generated image, and we also have our target image here. And then we pass these three images to the discriminator, and we get two probabilities. Whether the discriminator thinks the generated image is a real image, and whether it thinks that the real image is in fact a real image. So this is the discriminator architecture. If you watched the last video, you would understand this. And let's now go into what is the problem with this architecture and how can we solve it. The pix-to-pix architecture has a huge problem, and that is we often don't have datasets with paired images. So on the left here, I have a dataset of paired images, where for each image in the first domain, we have a matching image in the second domain. But the thing about this dataset is that it's very rare, and it's also expensive to acquire. Because if you think about this, we have to hire an artist to draw these edges, and we also have to hire an artist to, actually draw the realistic image in the second domain. And the same thing applies for all these other tasks as well. We have to manually create these black and white images, and we have to manually transform them into color images. We have to manually create these labels and get the facade images. So it's a lot of manual process, and that could be really expensive. So that's the big problem with paired datasets. On the other hand, what's more common is to have unpaired datasets. So in this dataset here, the X domain is images of landscapes, and the Y domain is images of paintings. So it's much more common to have these unpaired datasets where we just have a collection of images of landscapes and we have another collection of images of paintings. And we want to be able to create a generative architecture, which we can use these unpaired datasets to then generate new images of these domains. Currently, with the pix-to-pix architecture, we need a paired dataset. So we need to find an architecture that allows us to use these unpaired datasets. And that's where CycleGAN comes in. CycleGAN is an architecture which allows us to use these unpaired collections of images to generate new images. So let's now go into some of the details of the CycleGAN architecture. So in CycleGAN, We actually have two generators. And that's the really interesting thing about this, and the thing that sets us apart from Pix2Pix. Pix2Pix had one generator and one discriminator, whereas in CycleGAN, we actually have two generators and two discriminators. So we have two generators, G and F, and what G does, it takes images from domain X to domain Y, and F takes images from domain Y to domain X. So I have an image here, and we are going to train a CycleGAN network which can convert between zebras and horses. So given this image of a zebra, we can feed it into our G generator and it will produce an image of a horse. And also, given an image of a horse, we can give that to our F generator and it will translate that into an image of a zebra. So we're actually training two generators at the same time. And this allows us to go back and forth between these domains. So throughout this video, we're going to be using the example of zebras to horses and horses to zebras. So we'll set x equal to zebra and y equal to horse. So these are our two domains that we're working with. So G will take an image from the zebra domain to the horse domain, and F will take an image from the horse domain to a zebra domain. Now, with two generators, we also need two discriminators. Discriminator X is going to ask, is this image is this a real image of a zebra? So, given an image of a zebra, it's going to ask ourselves, is it a real image of a zebra? And similarly, D of Y, remember Y is our horse domain, is going to ask, is this a real image of a horse? So I think this diagram explains it very well. So we have our zebra domain here, which is X, and G is taking X to Y. So it's converting zebras to horses. And then we're going to feed that into D of Y, which asks, is this a real image of a horse? Similarly, we have our horse domain Y, and F is going to take that horse and translate it into a zebra. And then we're going to ask ourselves, is that zebra a real image of a zebra? So to summarize, we have four networks. G is going to translate a zebra to a horse, and dy is going to then ask, is this a real image of a horse? F is going to translate a horse to a zebra, and dx is going to ask, is this a real image of a zebra? One of the most crucial concepts of the CycleGAN architecture is something called cycle consistency. Now, if you think about it logically, let me give you this example. If I wanted to translate from English to French, I would have an English sentence and then I would translate it to French. If I wanted to take that French sentence and then translate it back to English, the two English translations should be the same. So the original English sentence and the final English translation should be the same. And that's what this cycle consistency is all about. So if I have an image of a zebra and G is going to take that image of a zebra and translate it to a horse, then I'll get this horse image. And then if I take this image of a horse and then feed it into our F generator, and remember F takes a horse and translates it into a zebra, we should get a zebra image that is the same as the original zebra image we started with. And this is what cycle consistency is all about. And this is what the CycleGAN actually enforces. It makes sure that this cycle consistency holds true. And the same thing goes for the other way around. If we start with an image of a horse and we go through F to produce an image of a zebra, and then we take that image of a zebra and we translate it into an image of a horse again, these two images should be the same. And that's what the CycleGAN actually enforces. And if you think about this, this actually solves the problem of mode collapse. If you don't know what mode collapse is, it's when a generator only outputs one image regardless of the input. So if we take this first example right here, to maintain cycle consistency, so to ensure that F, when it's given this image of horse, it can get the original image, that forces G to maintain the structural information of the original image. Because if this image changes, um, if it changes too much, then F will not be able to translate this into the original image. So it forces G to really understand and learn the structure of the original image. And the same goes for the reverse as well. So that's cycle consistency. Now let's talk about the loss functions of these networks. So since we have two generators and two discriminators, we're also going to have two adversarial losses. So G and dy are competing against each other, and this is the loss function of these two competing networks. If you've watched the previous videos on the pix-to-pix architecture and the GAN architecture, this will be familiar to you, so I'm not going to go through it again. We also have our F generator, which translates horses to zebras, and our DX discriminator, which checks if this is a real image of a zebra. And we have that corresponding loss function right there. So those are our two adversarial losses, which the generators, so in this case, the generator G would be trying to minimize this loss, and the discriminator Y would be trying to maximize this loss, while in this case, the generator F would be trying to minimize this loss, and the discriminator X would be trying to maximize this loss. Now, to ensure that we can maintain this cycle consistency, which we talked about, we also introduce a cycle consistency loss, which we're trying to minimize. So the first part of the cycle consistency loss is f of g of x minus x, and then we're taking the mean absolute error. Now, it might look a little confusing, so I've broken it down here. So this loss simply corresponds to the diagram we had before. So if you remember this diagram here, we're taking a zebra, translating it into a horse, and then to a zebra again. So that's exactly what we're doing here. A zebra to a horse to a zebra. So we start with the zebra X, we pass it through the generator G, that gives us a translation to a horse, which is G of X. And then we pass G of X to the generator F, and that gives us the result F of G of X, which should be a zebra. And F of G of X and X should be similar. They should look very similar. And that's what this cycle consistency ensures. So by taking the difference between these two, so that's the mean absolute error, and we're going to minimize that to ensure that um, these two these two ends of the translation actually are similar. And the same goes for the reverse case, so from horse to zebra to horse. So if we start with the horse image y, we pass that through the f generator, we get f of y, and then we pass that through the g generator, we get g of f of y. So we would want these two images, y and g of f of y, to be similar. So by subtracting them and calculating the mean absolute error and minimizing that error, we can ensure that they are similar. Okay, so we have the adversarial loss and the cycle consistency loss. Now we can formulate our full objective. So the full objective is going to be our adversarial loss for the zebra to horse, the adversarial loss for the horse to zebra, and our cycle consistency loss, which is weighted by this term lambda. And so this loss function, our generators are going to minimize this, and our discriminators are going to maximize this. Again, if this minimization maximization problem doesn't make complete sense, I would highly recommend you watch the previous videos on the pix-to-pix architecture and the GAN video, which was the first video in this playlist, where we really dive deep into the mathematics of this and how these minimization and maximization problems actually work out. Now that we have an understanding of the loss functions and how this CycleGAN is actually optimized, I think it's time to get into the architecture and see how this actually works. So if you've been following up to this point and you understand, the cycle consistency loss and the adversarial loss, and you've watched the previous video, this should be a breeze to get through. Okay, we start with our zebra image. This is X. We pass that through our generator G, and that gives us the zebra to horse translation. And pardon my expert drawing skills here, but yeah, I just had to flex. Um, all right, let's keep going. Okay, so we get that horse translation, but we're not done yet. We're gonna pass that horse translation, and we're gonna pass that to the F generator, and we're gonna get the zebra translation again. So we have this zebra, which we translate to the horse, and then we translate back to the zebra. And using these images, we can calculate our adversarial loss and our cycle consistency loss. So our adversarial loss, g of x, is going to be fed into the discriminator, and the discriminator y is going to ask, is this a real image of a horse? And the cycle consistency loss is going to say, well, if we go from zebra to horse to zebra, then the two zebras at the end should be similar. And that makes sense. So that's how we calculate that cycle consistency loss. And so this was from zebra to horse to zebra. And the same thing applies for horse to zebra to horse. So let's go through that as well. Um, Again, pardon my expert drawing skills here. Again, had to flex, but let's just keep going. Gosh, that's ugly. Okay, so we start with our horse image this time, which is our y, because it's from the horse domain, and we said the horse domain was the y domain. So we're gonna get that horse image. We're gonna pass it through our F generator, which translates that into a zebra, and then we're gonna pass that zebra translation through the G generator, which then gets us our horse translation. And using these images, we can calculate the adversarial loss. So with this zebra translation, we're going to pass that through our dx discriminator. And the discriminator is going to ask, is this a real image of a zebra? And again, to calculate our cycle consistency loss, we're going to ensure that if we're going from horse to zebra to horse, those two horses at the end should look similar. And that's what this cycle consistency loss ensures. So we would calculate these two losses, then backpropagate through the networks that we need to, and eventually over time, um, the translations won't look like absolute garbage like I drew them, um, but they will, start to look like actual translations from horse to zebra. And that is the CycleGAN architecture essentially done. Now, after you train the system, we will have two generators and two discriminators. As usual, we chuck away the discriminators and we're left with two generators that can map from domain X to domain Y and from domain Y to domain X. So I have some examples from the CycleGAN paper here. So in this example, they translated from winter Yosemite landscapes to summer Yosemite landscapes and vice versa. And they also translated from apples to oranges and from oranges to apples. Another use case is for photo enhancement. So you can take low res images and convert them into high res images. I think that's what they did here. Or I think they might have done a blurring effect, probably. Yeah, because this image looks like a blurred version of this. Either way, the possibilities of what you can do with image to image translation is pretty much unlimitless. All right, that is the CycleGAN architecture done. I just want to really remind you of the purpose of the CycleGAN architecture and why it is better than the Pix2Pix architecture. And that is that the Pix2Pix architecture needs a paired translation data. It needs a paired image data set. So it needs to have, those distinct X to Y pairs. But those data sets are hard to find and usually expensive to create. So that's why the CycleGAN architecture is really powerful. You can have just a collection of images in one domain and another collection of images in another domain, and those domains should be transferable. And then you can train this CycleGAN architecture to translate between those two domains. As for the next steps, I would highly recommend, again, going through the TensorFlow tutorial for this architecture. TensorFlow has a really great tutorial for CycleGAN, and in this tutorial, you actually implement a CycleGAN horse to zebra and zebra to horse architecture yourself. So you can, you know, build architecture yourself, learn about the loss functions, and maybe adapt this tutorial to a different use case which you might want to try out. Another thing I would highly recommend is that you read the paper, read the CycleGAN paper. If you've read the Pix2Pix paper and you also understand these videos that we've been going through, this will be a really nice read for you. It's really it builds up a lot of the concepts from the Pix2Pix paper. So if you've read that and understood it, this should be really easy to get through. And that's essentially it for this video. In the next video, we're going to be talking about stable diffusion and diffusion models, and that's basically a step up from generative models. So you take generative models and upgrade it, and you get diffusion models, and it's a whole new paradigm of thinking, and it solves a lot of problems that GANs actually have. So that's going to be exciting. If you like this video, send us a like. If you want to stay updated and get notified when the next video comes out, make sure you hit that subscribe button and also hit the notification bell so you get updated. Yeah, that's essentially it for this video. I hope you enjoyed, and laters.